This is the fourth and final section of the t-formulae chapter, and this is modelling with trigonometry. Now, the advantage with using the t-formulae for these types of problems is it takes something that could be quite a complex equation, a trigonometric equation, and it can be simplified quite nicely in terms of t, and you're able to analyze and see what's going on. So that's the whole purpose of using the t-formulae for these types of problems, is that you can analyze something that's in a much simpler form. Okay, so here we're given the displacement of a particle moving in a straight line. Its displacement is s, time is x seconds, and it's given by this expression here. And in part A, show that the velocity of the particle at x seconds is given by this expression here. Now, this links to a topic called variable acceleration. And with variable acceleration, basically, if we have the displacement and differentiate it with respect to time, so here time is x, we get the velocity. If you differentiate it with respect to time again, that's the displacement, we get the acceleration. And you can also get that by differentiating the velocity with respect to time. Okay, so this is going to be useful in this question. It's about differentiating. So part A means we need to differentiate the displacement s with respect to time, which is x. Now, I have choices here. I could use my t-formula and make the substitution here, then differentiate. Now, if we do that and we make the t substitution, we end up with something quite complicated. I'll show you what I mean. So there's another bit of information in this question. It says that t equals tan x. So I'll write that down. So if t is tan x, this means that everything doubles up then. So it means we're going to have expressions for sine 2x. So that's going to be 2t over 1 plus t squared. And we'll have an expression for cos 2x. And cos 2x will be 1 minus t squared over 1 plus t squared. So yeah, if we made the t substitutions first, so what we'll need to note is that here we need to replace that with the double angle for sine. So I'd have 2 sine x, or 2 sine 2x, cos 2x. So I'd have to make that substitution there, which means already I'm going to have this times by this, and then I'm going to have to try and differentiate it. So it's probably going to be a little bit more tricky that way, but it can be done. So I'm going to differentiate first, because this isn't particularly difficult to differentiate. It's quite straightforward. Then make the t substitution. So you always want to make things as straightforward as possible. So the velocity is going to be 4 cos 4x plus 4 cos 2x. Then the 2 is gone. Let me differentiate. Now I can substitute the cos 2x, no problem, because that's down here like that with t. But for this part here, I'm going to need a double angle. Now for double angles, we could use cos squared 2x minus sine squared 2x, or we could use 2 cos squared 2x minus 1, or 1 minus 2 sine squared 2x minus 1. So I just realized there should be a 2 there. Now, which one should we use? Well, if we use the first one, we know that we can just substitute all these t's in and probably simplify it. If I use the second or the third one, I'm not going to be able to substitute the 1 for anything, and I'll probably need to take this minus 1 off there, because that shouldn't be there as well. Yeah, if I substitute these in, I'm going to have this 1 that I'm going to have to deal with, this constant, which I may not be able to get rid of. I may need to multiply the 1 by something to get it into this form. Remember, it's always easier to start with something a bit more complicated and to simplify it. So I'm going to use the first one. Yeah, I'm sure it can be done with the second two, and I've tried it, but it's a lot more difficult because you end up with this number here and you're trying to get this number to try and fit here, and it doesn't quite work. Okay, so we'll go for that one. That one will always work. Yeah, so we'll write this down now as v equals, so this will be 4 cos squared 2x minus sine squared 2x plus 4 cos 2x. I can factorize out that 4, and I'll do that straight away. Always keep an eye on what you're trying to get to. So I see an 8 there, so I can at least take the 4 out. So that's part of the way there, and let's see what happens when we do that. So that'll be v equals 4, and then I will have my t substitution. So now I'm going to have the cos 2x, which is 1 minus t squared over 1 plus t squared, all squared, because that's cos squared, minus sine squared. So that will be 2t over 1 plus t squared, all squared, so that's my cos squared, plus, now I've taken the 4 out, so it's just cos 2x, which is 1 minus t squared over 1 plus t squared. Now I'm not going to close the bracket just yet, because if I have a look, this has been taken out as a factor, 1 plus t squared all squared. Now that's what I'd get as the denominator there when I square it out. That's what I'll get from the denominator from there, but I won't get it from here. So what I'm going to do is multiply the top and this bottom of this fraction by 1 plus t squared, and then it gives me that denominator of 1 plus t squared all squared. I can take that out as a factor. So if I do that, that will give me, so now I will have v equals 4 over 1 plus t squared all squared. So that's now as a factor. So all I'm left with now is the numerators, which is 1 minus t squared all squared minus 2t all squared plus 1 minus t squared times by 1 plus t squared, like that. Okay, so the rest now is just multiplying out that bracket and simplifying it. So let's do that. So hopefully there'll be a 2 that I can take out as well, because I need to have 8 out as a factor. Right, so let's multiply out all of these brackets in here. So from the first bracket I'll have 1 minus 2t squared plus t to the power 4. Second bracket, so that'll be minus 4t squared. Then for the last set of brackets, that's the difference of 2 squares. So that basically will be 1 minus t to the power 4. Right, so let's have a look. I've got t to the power 4 minus t to the power 4. Well, they cancel out. Then I will have 1, or well, the 1's will cancel out as well. Okay, and then all that's left is these 2 terms, like this. Actually, the 1's don't cancel out. I don't know why I said that. I thought it's a minus 1. So the 1's are there, so let me just circle those like that. So basically what I'll end up with in the brackets is 2 minus 6t squared. Now I can factorize out 2 from that, which allows me to put 8 on top of that fraction. And if I take that 2 out, all I'm left with then is 1 minus 3t squared, and we get the expression for v as required. Okay, so for part B, it says find the value of x between 0 and pi. Okay, that's probably going to restrict our solutions, so we need to keep an eye on that. For which the displacement is maximized. Okay, now we can find a maximum or minimum displacement by making v equal to 0. Okay, that's basically when it stops moving. That'll be the minimum or the maximum. To ensure that it's a minimum or a maximum displacement, we need to differentiate a second time, and then we look to see whether that's a greater than 0 or less than 0. And basically, if it's going to be a maximum, that means that that second derivative is going to be less than 0. So I'll just put that down here, that the second derivative, which will be ds squared over dx squared, at a maximum, that is going to be negative, it's going to be less than 0. Okay, now we've created a bit of space. First thing we need to do is to find out when v equals 0. Okay, so when v equals 0, so that will give us when 8 over this 1 plus t squared all squared times by 1 minus 3t squared, and that's equal to 0. That will be when the numerator equals 0, so that's basically 8 times by 1 minus 3t squared is equal to 0. So we can divide both sides by 8, so we'll have 1 minus 3t squared equals 0, which basically gives us t equal to, so if we take 1 away from both sides, or take 3 squared away from both sides, we get 3t squared equals 1, divide by 3, that'll be a third, square root that, so it's plus or minus the square root of a third, or 1 over root 3. That then means that tan x is going to give us plus or minus root 1 over root 3 or a third. So we'll just take this out here. We're going to need a little bit more space. So then we can use our calculators to work that out. So we'll do that in a second. Right, so doing the tan inverse of plus square root of a third gives us pi over 6. Negative square root of a third gives us negative pi over 6. Now if we use our class diagram to find the other solutions for this, okay, so I'll draw like a little one down here, I'll rub it out in a minute. So, whoops, let's try that again. Much better. So you've got pi over 6 here, negative pi over 6. So I can see that the other solutions are going to be either pi plus pi over 6 or pi minus pi over 6. So pi minus pi over 6 is 5 pi over 6. And pi plus pi over 6 is 7 pi over 6. Okay, now if we look at the range of solutions for x, it's got to be between 0 and pi, then straight away we can exclude some solutions. So we can exclude that one because that's less than 0, and we can exclude this one because it's more than pi. Okay, so that basically just leaves 2 values for x, and what we want to do is to work out which one of those 2 values is the one where the displacement is maximized. In other words, when d squared s over dx squared is less than 0. So we'll do that in a sec. I'll just clear some space at the bottom. Now, because we want to find the second derivative, now we could do what I suggested before. We could take this and we could make the t substitutions then differentiate. But if you do that, it does make it more complicated to do. It can be done, but I'm going to differentiate this first. Sorry, I'm going to make the substitution. No, I'll differentiate what I had from before. Don't want to get myself confused. So basically, do you remember from part A, we had this, that V equals, that was 4 cos 4x plus 4 cos 2x. Yeah. So sorry if I confused myself, confused you. Yeah, we're going to differentiate this, then make the t substitution. Not make the t substitution, which is basically this, and try and differentiate this, because you're going to need like the quotient rule in here to differentiate this in a chain rule. It does make it quite complex, so it's probably easier to differentiate that. So when we differentiate again, that's actually giving us the acceleration, but we'll write it as d squared s over dx squared, okay, which is basically dv over dx, which is the acceleration, and that is going to be, write a down, we'll just write down what it's going to be. So that will give us minus 16 sine 4x, and then minus 8 sine 2x. Now we're going to make the t substitution, because we want to substitute in t and see which one is less than 0. So we'll use the double angle here, because sine 4x is going to be 2 sine 2x cos 2x. We'll need a double angle for that. So that will give us, let's move this down a bit. Let's write it as a equals, so we'll have negative 16, and that's going to be times by 2 sine 2x cos 2x, and then minus 8 sine 2x. Now we can make our substitutions. So that will give us negative 16. So, and actually let's take the 2 out as well. And actually, what have we got? We can take out negative 8 from both of those. To put negative 8 there. I mean, it doesn't really matter, because we're just going to be substituting in, so it doesn't really make much difference. Anyway, yeah, if I took negative 8 out, so that will give me 4 times by sine 2x, which is 2t over 1 plus t squared, times by cos 2x, which will be 1 minus t squared, over 1 plus t squared, minus 8 sine 2x. No, we took the 8 out, didn't we? Took the minus 8 out, so that will be plus sine 2x, which will be 2t over 1 plus t squared. Now we substitute in our two values of t. So we've got either plus root third or minus a root third. Now we could just substitute in t's everywhere and see what happens. But if we sort of think about this, all of these denominators here have all got t squared. So the denominator of all of these, or the denominator of the whole thing, is going to be positive. So let's write that down. Denominator positive. So it's going to be the numerator that's going to decide whether this whole expression here is positive or negative. So we can just put negative or plus a root third into these, and then work out and these as well and work out which, just from the numerator, whether it's going to be positive or negative. So just working out the numerators just to save a bit of time. When t is the positive root a third, you actually end up with a negative answer. Okay, so your second derivative is less than 0. Let's use the right letters. D squared s over dx squared is less than 0. You end up with a negative answer. And when t is negative a third, again, when you put that into the numerator or into the whole thing, your second derivative, done it again, wrong letter, is greater than 0. Now we're interested when the displacement is maximized, and we said that is when this is true here, when it's less than 0, which is t equal a third. Now you may or may not remember t equal to third, when we did that, gave us this solution, x equals pi over 6. But if you didn't remember, you could also always go back and check and just say, well, here what this implies is that tan x equals this positive root third, and that gives you a value of x equal to this pi over 6. So then that would be our final solution for part B of this question. You should now be able to do exercise 5D on pages 125 to 126 of the textbook. I think I probably said this at the start, there's no new content here. This is just about taking what we know and using it to model different types of questions where we can use the t-formulae as a substitution to help us with the working. And these are the types of questions where you've got some sort of oscillation going on. So there's often sort of a graph that you need to look at and use that graph to help you decide what the period of the oscillation is. Look for where the sort of the main peaks appear, and that will help you then model the question and the working for it.